a node that's in a binary tree. And so there's two easy cases with, I really want to learn easy cases for node because if it's the leaf node, and then we have to deal with the fact that we the node that we're trying to delete has one or two children. And with two children is specifically the most difficult. So in this case, if we're just deleting all this stuff, this is pretty easy because we're just going to go through our binary search tree and look for that value. And if that value has a left and right set to 1, we know that it was
No.
what were the values of the left and right quantities for? So we know. So we know it's just a lead. That's super easy guys, like that. And so what you would do is just like in our linked list, if we were deleting the last item in the linked list, we would just set the pointer of the previous item to a null, and then we can just go ahead and free up that memory that that node is taking up. So this one right here isn't difficult at all. It actually is a pretty simple implementation. So that works great, yay. But so here we actually have to deal with more than a leaf node. But here, when we have a leaf node, we can go ahead and free up that data, the memory on those, so that we don't need to maintain it anymore. So we find the leaf node. How you accomplish that is you find the leaf node, and then you actually find its parent. And it's the parent that you need to update on those pointers to make sure that you set them to null, so that we know that we found the end of our tree at that leaf. Now, with deleting a node with one child, it's not as easy as deleting just the leaf node. The leaf node is pretty simple. But if you delete a node that has one child, then you've got to deal with the fact that that child has to be reassigned to somebody else. And so you need to actually, you find the value, then you need to go backward and find the value. Okay, so that's how we'll decide how to delete that node. So once we find the parent's pointer to that node, whether it's the left or the right, then we know which node needs to be deleted. And so what we're doing is really bringing the child of this node that needs to be deleted up one level. And so we want to make sure that we don't lose that connection. So here's an example where the node that we want to delete has one child, and so it's right here, the value of 4. So we got to do something with that too, okay? And so in this case, it's really not that hard because if you're doing a binary search tree, you know that any data to the left of the node that we are trying to delete on its parent, even if we had a second child here, what would the relationship of the data of the left and the right be to that node 6?
Less than.
It's still going to be less than. We're not going to corrupt our binary search tree by pulling those up one level because they already meet the requirements of the binary search tree that if the data that is below or to the left of our 6 is always going to be less than our 6 because that's what the rules say. So when you have a single node, a single child node, then it's pretty simple to go ahead and pull that guy up. So what you end up doing from a code perspective is we find a node that we want to delete. You got to check if it has children or not, because it is important whether or not they have children. And then here with the 6, we have to know its parent as well, because we have to be able to set up the relationship between 2 and 6 at this point. So what happens is from a deletion perspective, we will actually just reassign the pointer of 6, its left, to the node 2, and then we can go ahead and free up the 4 because we're done with it. So what that does for us is that left node has a left child, and it really doesn't matter if it's a left or a right, because the data value is still going to be less than what's sitting at its parent, 4's parent, which is 6. And so we just go ahead and delete and roll that node up to the next level. So here's deleting a node with one child. Okay, so this first one that we looked at was pretty easy because there wasn't a whole lot of structure below the nodes you want to delete. Because we only have that one child, and we only have to roll that one child up by 1, so that now the 6 its left is pointing to 2 instead of 4. So this one looks a little more complicated because now we have some more family structure down here below that actual node that we want to delete. But the good thing about the fact that the binary search tree, it doesn't matter that we're one node down further, we're still going to meet the requirements of what regarding 10 and the right. Everything on the right of 10 is what?
Oh, yeah.
It's greater than 10. So deleting this node 14 and he has his right is 18, all we would do is just change the relationship so that 10's right is pointing at 18 instead of 14, so that then we just go ahead and move that entire tree structure up one another. And so we don't have an issue here because this is pretty simple. But now the part that we have to worry about, which is a little more complicated, is having deleting a node with 2 children. So if we want to delete a node B, what do we do with it?
You have to compare the values of A and C to D to know where they go.
So you got to do a little more work with this one because we have to, how do we know which child node would replace B? It's kind of like, it depends, right? So if we look at you can't just update, D's left pointer and point it to A. You've lost the structure. Does that make sense? You can't just say, all right, D's left now A. That's not going to work. Because what happens to C? I mean, it just then kind of loses itself. I mean, it's completely unfortunate. It doesn't follow any paradigm that we're supposed to do. So then we need to look at this in more in detail. So here the example is we want to delete node 18. So when you're looking at that, when you're looking at a node that has 2 children, you need to look at its left and its right. And you need to try and figure out which one we would replace that with. Well, thank goodness there's some basic rules that say how you would do this. So when you're looking at deleting a node that has a left and a right and has 2 children, so we have to determine which value we can put in place of 18 and maintain the overall structure of our binary search tree. We do that by finding the maximum value on our left. So our maximum value on the left is 15. And then we find the minimum value in the right. And on the right, our minimum value is 25. So again, we're doing the max value on the left and the min value on the right. So that's how we would determine which node we're going to use to replace 18 with. Which one you choose actually is not a really big deal, but we do have to follow a process on how we get there. So deleting a node with 2 children. If we want to get rid of 18, so our possible nodes that can go in 18's position is either the largest value on its left child or the smallest value on the right child. And then we just pick one of those values and copy it in there. And so what we have to do is first we have to actually copy that node in there. So for a moment there, you'll have 2 instances of 15, and then you actually delete that and keep node of the 15. So the rules tell us that we've got to find the children until we find a leaf, and then we'll compare the data values of the children and see who is our min on the right and our max on the left. By doing this, this means that we are going to absolutely positively make sure that we have maintained the integrity of our overall binary search tree. And so how can we guarantee that that is actually going to happen? Because the node on the left subtree, it cannot have 2 children of its own because it would cause a situation where one of them is greater than what we're using. So it's got to be a leaf node so that we don't run into that problem. And then if you're going to use the right, then we need to find the smallest one on the right, and it cannot have 2 children because if it did, then its left is not going to follow the actual relationship that is enforced when it comes to binary search trees. So if we look at this for perspective of, let's say we decided to use 15, okay? So we start here on the left on, we searched our binary tree to find the largest value on the left and the smallest value on the right of 18, that is a leaf node. And so as we look at that, from a visual perspective, it's pretty easy because you look at all 15 and 25, so those are my values. And so what happens here is you look at that data, you look at it, it's two options. If I move 15 to 18, does it maintain the integrity of my binary search tree? Does it still follow all the rules? It does, doesn't it? Because if you put a 15 in there instead of 18, 13 is less than. Yes, sir.
Is it completely ambiguous if you choose the maximum left or minimum right, or is there an advantage to one or the other?
There is not. It's just a preference. So usually with some, you'll be given guidance or something saying specifically which one you're supposed to pick. So from this perspective here, if we're looking at the left, then our largest value on the left is a 15. So if we plug that 15 into where the 18 currently exists, then we have maintained the integrity of our binary search tree because on the left, the 13 is less than 15 and the 10 is less than 15. And so we're totally fine here. And then on the right, if we pick 25, we see that if we plug 25 in there, 32 is greater than 25 and 43 is greater than 33. So we 32, excuse me. So we maintain our integrity. And so again, on the left, when you're dealing with deleting a node that has two children, you've got to find the largest value on the left, that is a leaf, and the smallest value on the right, that is a leaf. So here, when we look at it from a 25 perspective, he would also work because he is the smallest value in the right subtree. So here, he is a logical predecessor to it, and so we can go ahead and look at using him. And then at this point here, it's also a logical predecessor. So here, when we delete that node, so we've got to copy the replacement node into the node that we want to replace. And so how do we do this? And if they're not leaf nodes, then, or they only have one children, you have to guarantee there's at least at most one kid. And it's still pretty easy. We're just going to roll this up one level. That's what that. All right. So there's a lot going on for the deletion. It seems pretty easy from a visual perspective, but from a food perspective, it's going to take a lot more work. And so what you see is you're going to have a lot of extra functions running around that make all of this happen for us. And so first of all, we have the find node function. And so we got to find the value that we got to find that value in our binary search tree that we want to delete. Because if we don't even find it, there's no point in bothering, right? So then we have to know who its parent is, because it's the parent we're going to update his pointers. So we need to know who the parent to that node is. Then we have to search for our min value to find the minimum value on any given binary tree. We need to find a maximum value on any given binary tree, whether or not it's a leaf node. Is there only one child? Is it only the left or is it only the right? So if it only has one child, we would want to know that relationship. So here's where you're going to end up running a lot of helper functions or auxiliary functions. So the first one is this find node. And so first of all, you've got to find where in the binary tree search that specific value exists. And so you're just doing a search function, and you're going to go ahead and look for that value. And then here, we need to find out if we find it, then we need to know if it has children or not. So the find node here first returns a pointer to a node that actually stores that value. So here we have our return. So this implementation returns back a pointer to where it finds that node. And here, so we do our find node, and we pass in the pointer to our array, our binary search tree, and then we also pass in the value that we're searching for. And so here, if we find that value in the roots, then we're just going to go ahead and return that guy because of the analytic case. And then we have searching to our right, and that would be also to find that value. So we're going through this in order to find where is our node. If we end up through this whole process and we never find that node anywhere, that means that that value doesn't exist in our binary search tree. So the parent, we need to find the parent of that node. And so we know the parent of who we want to be. Because without that, if we don't fix that relationship between the parent and then the next level down, we're going to lose a whole bunch of nodes. And so here, it just lets us modify our left and right pointer to the parent. So, you're already you're breaking that relationship where it was pointing at the node you wanted to delete, and it's going to update it to the new structure. So here, then, the arguments for this function are the root of the tree and are pointed to the node that we want to find the parent of. And if you find the parent, we want to set back his pointer. So here you see we have this function, and you see it returns a pointer to the node, and it's called parent. It receives the tree structure, the root node, and then another instance of that node of the value we want to actually delete. So first, we got to deal with whether or not everything's null. Because if it is, then if it's null, that means what? We don't even have anything in our binary search tree, do we? If it's null, okay? And then here, if the root equals the node. If the root equals the node, what does that mean? What does that tell you about your binary search tree?
It's only a one.
There's only one element in it. So if we're going to delete that one element, we're done, okay? So that's pretty easy. So if that doesn't happen, then what we need to look at is the root. Is the root the direct parent of the node that we want? So does the pointer to root's left equal that node that we're trying to delete? So it's looking at that relationship. Or is it the root's right node? So is it directly below the root? So from a visual perspective, it's looking for this relationship right here. So 59 is our root. His left is 25. His right is 67. So from a code perspective, what we're looking at is this relationship right here that existed. It had our 59 pointing to our 18. Our 18 is who we wanted to delete. So that situation is taken care of here, where we're looking to see if the root is the direct parent of that node. And so if it is, we're going to go ahead and return the root. Because again, we're looking for the parent of the node that we want to actually delete. So if that's not the case, so now we're going to look for the node's parent in the left side of our tree. So we're going to keep traversing the left to see if we can find it. And so here we're checking our node data, and is it less than the root data? So why am I checking if the data I have is less than the root data? Which way is that going to take us on that tree?
Right.
If it's less than, then it's left. Okay? So this is giving us the opportunity to recursively search the left side of the root for the value we're trying to delete. Otherwise, if it's greater than, then it must be on the right of our root node. Otherwise, we're going to just return a null because there is no relationship happening based on the overall evaluation here. So we're looking for, first of all, we're looking to see if we're either null or the node is the same as the root. I mean, there's only one element in our binary search tree, so we just go ahead and reset that. Otherwise, we need to start looking to the left or to the right to determine if it is a direct child of our parent node, because that's pretty simple. Because all we would do is just update that pointer to get rid of the child, right? So then here, otherwise, it's got to be buried somewhere in our left and our right. So we look at our left and we look at our right to see if we can find that root node. So we have the node we want to delete. We found out that it really does exist in our tree. We found out who its parent was. So now that we know where the node is and who the parent is, Now we've got to come up with who are we replacing it with. So here is the min value. If we want to find the minimum value of any given binary tree, you have to be careful when you're trying to delete those nodes with two children, because we need to know who we are going to replace it with. And it doesn't matter if you replace it with the minimum value on the right or the maximum value on the left. You just pick one as your implementation. And so this argument for this for the function is between the tree, and it just returns back a pointer to the node that contains that smallest value. So let's look at this list again. So deleting a node with two children. So first you find your node. We found the parent. Now we're finding the minimum value on the right, and we're going to find the max value on the left to allow us to update our binary search tree.
And it doesn't matter if it's vice versa even. Okay.
Mm-hmm. Does not matter. They both give you the same result. So if we find the min value in any this function here allows us to find that min value. So here we're going to pass in our group, and we're going to start looking at our binary search tree, and if we're looking for the min value. So first of all, we're going to see if our group's left is null. If it's null, then what? Yes.
Is this really faster than just copying it into a buffer, deleting the data, and then redoing the tree?
How would you copy it into a buffer?
Or you just go down like close to
The confusion that I'm seeing so far was close. No one's
and
assigned
then
yet.
just remake the tree. From scratch.
Are you going to guarantee the relationship?
But I mean, if the order didn't matter, if you're switching on the data anyway, as long as
Well, the order does matter. So if you put this into
No, hold on.
an array, if you put that into the array, how would you store it?
It still shows stuff.
well, you would just store the individual data and then create the tree from scratch.
But it was content.
You don't think the nodes move?
It was
But
content.
as long as they're following the same rules, it doesn't matter.
No, it's not the main thing, it's more about the architecture of it.
Yeah, it is. Yeah, this one.
Yeah.
I had that class. I think it's my dad's. Yeah. It's interesting.
I'm not sure that we would be able to recreate a tree by just showing it in the array.
I mean, as long as you keep the root, the main of the root, it should
Tell you what,
still
bro.
divide.
What's your program that you want to write?
What would it look like this when it was done?
Oh,
If you're moving the last node, it shouldn't matter the order. If you're just switching 25 to 18, as long as they're separated the same.
Because in what order are you planting the nodes in
Yeah.
the array? Because if you're doing, say, like pre-order, and you're putting like 59, sorry, like 10,
I'm not gonna,
you get 10, 13, 15, 18.
I mean, I'd have to like see the code or, at least see your pseudocode on it. I'm not 100% confident that just populating an array with a data that already exists to make it lay that out this way. You might end up in a different order. So I'm just saying, I'm not sure how you maintain the integrity of the order that's there. Does that make sense, or?
Wait, so does the order really matter if you're taking 25 to the bottom and throwing over 18?
The order you put in the array will determine which is the first node on the tree, and from there, you're putting the next two nodes. But what you're doing, what order are you storing the first data?
I mean, you would have to know specifically where this data lives before you deleted that, deleted that node. Because what, changing the relationship,
You're changing the relationship doing it this way. You're taking 25 that's a leaf node and making it a parent.
It's a localized change.
still good to see.
For example, if you don't put 59 as your first item in the array, what's to say that 25 is a new week node, or 18, 67? It all depends on your index 0 of your array is going to determine how your new binary system starts.
Professor White,
Yes.
in this for homework, experimental with this, is you do a breadth first reversal, and then if you print out all of that out and create your binary tree again, then it'll be very, very late out. But when Jonathan said, it won't be as efficient as just doing it normally. Like how you're talking about that.
Because what I'm saying here is, yes, we're replacing 18 with 25, but we haven't modified the relationship a little bit at all. We still have the 13 and 10. But I keep the last, right? So unless we do what he says, and specifically copy it into an array from a first perspective, then that would actually maintain that relationship. What I'm saying is, we don't want to change the relationship so that you end up with 15, then 13, and then 10. You know what I'm saying? Whatever we're rolling up by one level, we can't modify those values. So 13 and 32 and 62 and 72 still need to be on level 2. But he's saying that abrupt first, okay, then that would maintain that relationship. So now we're back to the question of efficiency. Is it efficient to copy all the data into an array from a abrupt first perspective, swap out the guys we need to, replace the 25, replace the 18 to 25, and then roll it back out? Is that more efficient than what the other modalities implement? So that was Jonathan's saying that probably not more efficient, and you agree that it's okay. So technically, yes, it is based on what we discussed. Now for the efficiency, yeah. I have to write myself to say for sure which one is most efficient. But yeah, so your idea would work as long as you did that. And you maintain that order. The thing that we don't want to do is change the order that, we don't want to change that 13 as the left, that 10 and 15 as 13 children. We don't want to change that 67 as the right, and that 62 and 72 are his children. Does that make sense? Yeah. So I don't think, so if you came up with a solution that potentially changed the relationship between our nodes, we create a binary tree, yes, that's correct. But I'm sure there's some rules out there that say you can't. But I haven't come across anything that says that specifically, that we have to maintain this relationship, but that seems to be the intent. Okay. So again, you're going to do the same thing. You're going to find the largest value on your left and the smallest value on your right, and determine which one to use. So if our largest value on our left is 43, we'll still maintain our current binary search tree because 43 is greater than 18 and everything else on the left. Or over here, our max value on the right is 72. Our min value on the right is 63. So the 63 up there in place of 59, it still is a valid binary. Yes, and not there. So you find the max value on your left, the min value on the right. It's the only way you can maintain that structure. That make sense? Yeah. Okay, so what we're talking about is how do you know who to replace with. So first we're going to find the minimum value in a binary tree. We're going to find our max value in a binary tree. We also need to find out if a node is a leaf. So let's walk through this. So first we did the find. We found who his parent is. We found that minimum value. So here, when we delete a node with two children, we know that we've got to replace it with either the minimum value in the right subtree or the maximum value in the left subtree. And so that's what these functions are doing for us. And it just returns a pointer to those values. So here's the method, here's the function for finding your min. So you pass in your root and you are going to start looking through your value. So if our root left is null, that means that we don't have a left on our root. And then here, otherwise, we're going to look at the left to find that minimum value. So that minimum value is very specific to looking to the entire left of your binary tree, binary chemistry. So maybe because min value would almost be misleading. I would say min left value for my purposes, but so here our max value, again, we're looking to the right now. So here we're going to check roots right and see if it's null. If it's null, we don't have a right. Otherwise, we're going to use recursion to keep checking for the max value on our right of our binary tree. So we do care if it's a leaf or not, because that means that we don't have any children if the node that we find to delete is a leaf. Then we know we don't have to worry about any of the relationships of its parent to any children. And so that makes it pretty easy to do that delete. Or if we only have a left child. So here we're going to check to see if we only have a left child. And so we're going to keep checking for whether or not the left is not equal to null and the right is not equal to null. Because it's equal to null. So we're checking here if it's a left-only child. If it's a left-only child, that means you have your left pointer is pointing to a node and your right pointer is null. Now we have the same thing, but on the opposite. Is it a right-only child? So here, a right-only child would mean that our left is null, but our right is not null. And so that means that we have a right-only child with our relationship in our binary search tree. So from this perspective, let's actually look at some code. Oh, wait, I got something really funny for you. Okay, so do you want to see why I quit working in the industry? I told you I worked on a call for fire trader, right? So we had this legacy code, and I was trying to fix it because it was broke. Okay, so what happens is in the real world, when you're military, you do artillery. All right, so a unit usually has 3 huge, big-ass guns, and then we have some big-ass shells that go with those big-ass guns that takes out shit like tanks and all that, okay? So what happens is normally what happens with the guns is the way the gun is set up, it has 6 rounds in it. I mean, I'm talking about rounds that like are as big as you and I. They're not small, okay? So what happens is let's say you have a target acquired and you are trying to obliterate that target, and big ass shells are really expensive. So you don't want to waste them. I mean, it's fun to shoot shit up, but you don't want to waste them. They're worth a lot of money. And so what you have to do is you have this opportunity for a ceasefire. So like you launch a couple of volleys and then you're like, oh, we wiped them out. We're done. Ceasefire. Stop shooting. Okay. So what was happening with this code was that even when I put in a ceasefire, it kept shooting all the other volleys. So let's say we shot 2 volleys and then it kept going. We're like, oh, screw you. I'm killing the guy. Okay. The reason why. And this is the only thing ever in my entire life of programming I could not fix. So, first of all, let's look at the bottom. This is 1.1.c++ file. What is that number to the left? That is lines of code, people. This is one file. All right, this was my albatross in life. And this is only half of what it used to be when I first started working on it. It was 30,000 lines of code in a single file. Holy hell, okay? So I lost hours of sleep, probably killed a lot of brain cells trying to make this happen. So the problem with this code here, holy shit, the problem with this code here is what happens, and you'll love this. Have you guys worked with threads at all? You understand what threading is? At least understand the concept of threading? And so you can do multiprocessing, you do more than one thing at a time, right? Okay. So what these 13,000 lines of code are doing, which I just love it. Pretty sure this is why I quit my last job. So what happens here out in the real world, when you're playing with guns, all right, so this is the enemy, and you are the friendly. So friendly is always blue, enemy is always red. So you got some little dude out there. He's got his little binoculars. He's like, yep, spotted the enemy. And then you give them their latitude, longitude. So let's say it's at 32 Bravo Light Tango at this easting, this northing, and this easting. Okay, so this is just a latitude, longitude location on the ground. So they've got their 3 big ass guns here. Each one of them gets 6 volleys. So let's say that I hit 1 launch, 2, 3, and we blew him up. So he's done. So we want to do a ceasefire. Okay? We don't want to waste the guns. There are so many threads in this application right here that it threaded itself to death. Okay, so here is, this is just a sleep. So what's happening with this code, and the reason why I actually could not fix it, is because I could not interrupt threads. So what happens is, there's a thread for this overall unit. And this unit has 3 guns, so each gun gets its own thread. So we have a thread that's a parent of 3 threads. Each gun has 6 volleys, so each gun gets 6 threads. These are all running simultaneously, mind you. So think about parallel processing. We're parallel processing 18 threads at one time. You cannot interrupt that shit. I tried everything I could possibly do, and I absolutely could not fix this code. I could not make that ceasefire happen because I couldn't kill the threads. It wouldn't stop. You keep seeing the little volleys go over and over, and you're like, Whiskey Tango Foxtrot, why isn't it stopping? I killed the thread, it should have died. Okay? No. So, I always toy with the idea of giving this out as an assignment into the class and ask you guys to rewrite it. And then people look at me like, you are batshit crazy woman. No, okay? I'll just drop your class and take it when you're not teaching it. Okay, so this is probably the worst programming I've ever seen in my life. It is absolutely atrocious. Horrible. Horrible code. Yes, ceasefire right here. Basically, this file just goes screw you. Nope. Nope. I'm going anyway. Alright, so I like to show people this. This is real world, absolutely horrible programming. Now, the thing that really hurts my feelings as a professor at UCF is a CS student who graduated from UCF wrote this shit.
Oh, shit.
Okay, so clearly before we all got here, there are some really bad professors. No, it's not. It's not our fault. We can't help it. But yes, so this is fabulous. And for those of you that don't think that you will ever use physics, I can tell you that this, the processing of how a gun shoots a shell and how it actually hits its target is all physics. All physics.
That's obvious, yeah.
What's that?
Projectile motions.
Yes, projectile motion.
Yeah.
We use it in the real world. So you really do care about that stuff. You're like, what? I'm never going to use this again. Yeah, you are. Okay, so
Fixes everywhere, to be honest with you.
go look at the code on what courses. I have my code example up there already for the binary tree stuff. And just take a look at that, because it'll help you
Physics is almost.
tremendously with your assignment form. Have a good day.
It's the universal science.